So I want to continue talking about reasons to be interested in models of noisy cognition, but in this lecture I now want to go into one specific application of that idea in more detail, and this is to some extent already previewed in my more general remarks in the first lecture, which is that I want to particularly talk about thinking of the way that people make decisions about risky gambles. So just to recall, I mean, in the first lecture, I've introduced the idea that choices might be based on imprecise internal representations of the choice situation rather than being based on the exact data that has been presented to the decision maker. And I've argued that this is something that could provide an explanation, not just for the thing we started with, which was trial-to-trial variability in responses, but also for systematic biases in the way choice options are valued. And the idea is that if the decision is going to have to be based on a noisy representation, then an optimal decision rule is one that is going to be based on an optimal estimate of the value of the item based on this noisy reading of the data. That optimal estimate will be a Bayesian estimate conditioning on the evidence that's provided by the noisy representation, and then also taking into account a prior that the decision maker has about the set of decision situations that they might be facing. But this optimal Bayesian estimate need not be equal, even on average, to the true value that was being encoded with noise. And this approach of assuming that judgments, estimation of magnitudes in the case of sensory magnitudes might be viewed as optimal estimates based on noisy sensory information has turned out to be fruitful in understanding perceptual biases in a variety of perceptual domains. And I think this then is a possible explanation for many types of behavioral regularities that are commonly taken as an aspect of people's preferences, or are explained by hypothesizing that the behavioral regularities show that people are simply executing some kind of suboptimal heuristic. And instead, I want to propose that a different line of explanation might be that people are behaving in a way that doesn't involve some exotic kind of preference and doesn't involve a failure to respond in a more or less efficient way to the situation they're in, or to the noisy representation that they have of the situation that they're in, but that it may be the limited precision of their internal representation of the situation that is the issue. This is not so different from the kind of perspective that Eric was presenting in his earlier talk. I mean, if I were going to describe, my view of the hypothesis he was presenting, it would be that people have an imprecise understanding of the decision problem they're facing, and they don't accurately distinguish the situation in which there is zero probability of the early arrival of the rewards from the environments that they may often have encountered in which there is some positive probability of the early arrival. And so one could think of them as, in fact, implementing an optimal decision rule conditional on this imprecise representation of what the situation is that they're in. In any event, I'm not going to go further on intertemporal choices in this lecture, but I think that this is a possible explanation for a lot of types of regularities that have often been treated in the literature as aspects of preferences, maybe funny kinds of preferences, that one might instead view them as optimal adaptations to cognitive noise. In this lecture, I want to illustrate that possibility in the context of choice under risk, and I'll be talking in particular about recent work that I've done with Mel Kaw and Zhang Li in a couple of recent papers. Okay, so I want to talk about how we understand people's attitudes toward risk and in particular the fact that people don't behave in a perfectly risk-neutral way. And of course the fact that people often make decisions under risk that aren't consistent with perfect risk-neutral valuations is a very old observation. Early in the development of probability theory, mathematicians were interested in applying probability theory to understanding gambling behavior, and it was observed very early, even early in the 18th century, that it was quite common for people not to make decisions about whether to take gambles or not simply on the basis of whether or not they were mathematically fair bets, so as a perfect risk-neutral decision maker should do. And of course, there's a standard explanation that we teach undergraduates about how we can understand departures from risk-neutral behavior, which is that people seek to maximize their expected utility from wealth rather than the mathematical expectation of their wealth itself. And if utility of wealth should be an increasing function of wealth, but a nonlinear function, then maximizing expected utility of wealth does not mean that you're going to maximize the expected value of your wealth, and therefore that you would not take gambles if and only if they're mathematically fair. So Bernoulli had a famous explanation of risk aversion on this basis, hypothesizing that the utility of wealth should be a concave function, and he suggested the logarithm as a plausible function even. But it's also well known that you could explain risk-seeking behavior under some circumstances with a theory of this kind if you assume the utility of wealth isn't always concave over the entire range. Famous paper by Milton Friedman and Jimmy Savage back in the 1940s wanted to explain why people often are willing to play lotteries that are not mathematically fair bets, and they nonetheless buy the lottery tickets. And their hypothesis that was that perhaps many people had a utility of wealth function that had a convex range, and that if you were in that range, certain kinds of gambles could indeed be expected utility maximizing, even if they had a negative expected value. Okay, so that's a familiar kind of explanation of departures from risk neutrality, but I think there are some problems with thinking that that explains everything that we observe about choices under risk. So one simple thing that I've already mentioned that theory by itself doesn't give you an answer to is that kind of theory still implies there should be a definite preference ordering between any two risky options. Instead, observed choices seem to have a random element to them, as I talked about in the previous lecture. A common response is to say, well, you can add a random term to the calculation, like in additive random utility models of stochastic choice. I think that has to be viewed as reflecting random error in the value comparison process. So a possible interpretation is say, well, no, the preferences just themselves are randomly variable over time, but I don't think that in something like the Mosteller and Noji experiment, it makes sense to say that what's going on is that subject has well-defined preferences at each point in time, and they understand them perfectly well, and they're making coherent decisions using their von Neumann-Morgenstern utility function at that instant, but there's random variation in what their von Neumann-Morgenstern utility function is. It means, sometimes that same subject was sometimes risk-averse, sometimes risk-seeking, risk-averse and risk-seeking to different amounts over the course of a relatively short experimental session. I think, the randomness has to be viewed as random error of some kind in their decision process, and so if you are using a model that adds a random term to the expected utility calculated for the gamble, you have to view that as error in the comparison process. Okay, that's a coherent theory, but I think if you're willing to admit that there's random error in the comparison of these values, then when making the decision, it's not obvious why you should think there's random noise in the value comparison stage in the process, but no possibility of random errors in any of the cognitive processing that occurs earlier. Why not imagine that there could very well be non-trivial amounts of cognitive error earlier in the processing of the information about the different gambles, and that's indeed what I'm going to explore in this lecture. Another problem with the nonlinear utility explanation of what we see is that if risk aversion is due to diminishing marginal utility of wealth, then it should become negligible in the case of small enough stakes. And instead, what is often observed is a non-trivial degree of aversion to better than fair bets, even when the stakes are quite small. And Matt Rabin has discussed this problem with expected utility maximization in detail. This is showing you again the Mosteller and Noji data. You may not have thought there was anything shocking about the degree of risk aversion apparently present in this subject's data when I showed you the data before. I showed you how they estimate the indifference point. X, the payoff of the lottery required for indifference, is a little better than a fair bet. Right? A fair bet, mathematically fair bet would be here. You get 10 cents for probably 1/2. You pay 5 cents to get it. And mathematically fair, it seems like it needs to be about 10.7 cents instead of 10 cents. But you might say, well, okay, that's a little bit of risk aversion. A little bit of concavity of the utility of wealth function can explain that, so that's perfectly consistent with standard theory. If you ask how curved does the utility function of wealth have to be to explain that, you conclude that the amount by which your utility is increased by gaining 5.5 cents must be a bit smaller than the amount that your utility of wealth is decreased by losing 5 cents, right? Because that says when it's only 10.5, you're still to the left of the indifference point. And okay, well you say, okay, I believe that. Diminishing marginal utility of wealth, that's fine. But that was, 5.5 cents and 5 cents already. The utility of wealth function is bending enough for that to be true. You can ask, well, suppose you think that's uniformly true, that when you had a little more wealth or a little less wealth, it would continue to be the case that the opportunity to get 10.5 cents with a 50% probability is not as valuable to you as having your 5 cents with certainty. You would be able to conclude that the utility loss from losing $1 is bigger than the utility gain from gaining an unbounded amount of wealth. And then if you ask, and so then the theory would imply that someone offered a bet where you have a 50% chance of getting, $10 trillion, but there's a 50% probability of losing $1. It would predict that people would more often than not turn it down. You probably don't believe that, right? That of yourselves, at least. So now you don't. That's. So suppose I say it's just $1 trillion. It's just $1 trillion, and it's the U.S. government that's going to say they could actually come up with $1 trillion. But anyway, that I think that is actually a shocking degree of risk aversion, in my view, if one interprets it as coming from diminishing marginal utility of wealth. Okay, well, so there's a common response to that in the experimental literature as well, which is say, well, in fact, people don't maximize the expected utility of their total wealth, integrating their earnings from that experiment with the rest of their lifetime budget constraint. Instead, they have a nonlinear utility function for the earnings from this particular gamble in isolation. And okay, so then you could assume there's enough curvature in that function that's evaluating how much you like different possible outcomes from this individual gamble. But you have to ask, so if those are considered the true preferences, well-considered preferences of the decision maker, I mean, it seems kind of odd to think that that is what people genuinely prefer when they understand what they're choosing. It's certainly not consistent with the view that the reason you care about money is because of what you can do with it. Because in terms of what you can do with money, you should integrate your earnings of $1 or whatever it is from some small gamble with the other dollars you have from other places. There's not a reason for significantly diminishing marginal utility of this particular dollar, which only buys the same kind of things for you as all the other dollars that you can get from other things. The proposal that I want to make instead is that this failure to perfectly integrate the earnings from this individual choice with the rest of your wealth is going to be a natural consequence of assuming that the decision is based on an imprecise mental representation of the data that you have. And I'm going to propose a theory which doesn't assume that you care intrinsically about wealth that you obtain from this experiment differently from how it contributes to your overall budget, but it's the fact that the data about what you can get from this particular gamble is being presented separately. In other words, someone's not telling you about your overall lifetime wealth if you do or do not take the gamble. They're telling you about the payoffs from the different choices you face in the decision problem. That's going to be, by hypothesis, is going to be imprecisely represented mentally. You can form an estimate now of the consequences for your overall lifetime budget of making the different decisions, but you're going to make the decision based on that noisy internal representation of what you know about the individual gamble. It's going to produce behavior that looks as if you're applying some nonlinear function to gains or losses in the individual gamble instead of correctly integrating it with the rest of your wealth. And finally, maybe a particularly obvious problem for the nonlinear utility explanation, the same subjects can be observed to make both risk-averse and risk-seeking choices depending on what kind of decision problem you offer them. And that's something that Kahneman and Tversky make quite a bit of in their arguments against expected utility theory and in proposing prospect theory. And so I've pointed out that expected utility theory is consistent with, gives you an explanation for risk-averse choice. It could give you an explanation for risk-seeking choices as well, as Friedman and Savage pointed out, but it doesn't explain why the same subject shouldn't either be at a locally concave point on their utility of wealth function or at a locally convex point on their utility of wealth function. And so for all small enough gambles, they should either always be risk-averse for all small enough gambles or always be risk-seeking for all small enough gambles, but you shouldn't be able to present them with different small gambles and get them to be significantly risk-averse for some of them and significantly risk-seeking for others of them, and that's the kind of thing that Kahneman and Tversky find. I showed you some evidence from Enke and Graeber of that kind already in the last lecture, where you were seeing how both risk aversion and risk seeking could show up depending on whether the probabilities were small probabilities of payoff or larger probabilities of payoff on the gamble, and so that's not consistent with any nonlinear utility of wealth function. So in terms of what kinds of combinations of risk-seeking and risk aversion you see in the same subjects. Tversky and Kahneman have a 1992 paper that documents this fourfold pattern of risk attitudes that we were talking about before. Their experiment does involve eliciting certainty equivalent values for simple lotteries of this form, that they're specified by a probability P of getting a non-zero outcome X, otherwise you get 0. What they find, the so-called fourfold pattern, is that when the probability of the non-zero payoff is large and it's a gain, the certainty equivalent is between 0 and the expected value, so that's risk-averse valuation. But instead you have a risk-seeking valuation if the probability is a small positive probability, and again it's a random gain. This switches, so that's the switching from risk aversion to risk seeking, but they also then find risk seeking behavior if it's a large probability of a loss, but risk averse behavior if it's a small probability of a loss. So that's the 4 different patterns they proposed. They don't argue that the ratio of the certainty equivalent to the expected value has much dependence on the stake size. They think it mainly depends on whether the probability P of the non-zero outcome is large or small, and they interpret that variation as reflecting what they call a nonlinear probability weighting function, that the importance of the different outcomes in the decision rule is using a weight which is different, is some kind of nonlinear transformation of the probability P. But there are other kinds of patterns that have been discussed in the literature as well. Markowitz, in an earlier paper back in the 1950s, also argued for a fourfold pattern of risk attitudes that involve people sometimes making risk-averse choices and other times making risk-seeking choices. His pattern was, he argued, that people are typically risk-seeking with respect to random gains when the stakes are small, but become risk-averse with respect to random gains when the stakes are larger. Instead, risk-averse with respect to losses when the stakes are small, becoming risk-seeking with respect to losses when the stakes are larger. He had a theory of how that could happen, which is that people maximized the expected value of a utility function for net gains from a gamble, which was kind of a complicated function. First convex for very negative, large losses, then concave over a region of smaller losses, then convex again over a region of small gains, and then concave again over larger gains. The point is you need some kind of nonlinear transformation of the net gains as well as the idea of a possible nonlinear transformation of probabilities to account for all of the kinds of patterns that we see. You can think of nonlinear transformations that can reconcile these different patterns, but that raises a question of why people would base their decisions on distorted values of the data instead of on the exact values. If you think they correctly perceive the exact values and have access to that in their decision process, you might ask why evolution should have favored a use of that information that bases the decision on nonlinear distortions rather than on the actual values, which would then allow them to more accurately recognize the value of these options to them. Another question that I think prospect theory and theories like that, Markowitz's theory as well, raise is that if you think there are these nonlinear transducers that have transformed the objective data and that are then going to explain observed behavior, an important question, I think, is whether we should expect those nonlinear transducers to involve parameters that we should expect to remain invariant across environments or not. So we can say, well, maybe some kind of experiment we can explain what people are doing with our particular nonlinear transformations, but if we don't understand what the logic is of where it would come from, we might ask whether we should expect it to be stable across environments or not. Finally, I think an important question is whether we can use these, if we think that these are people's preferences, maybe exotic preferences, but we're actually estimating what their preferences over gambles are like, should we use those estimated preferences as a basis for welfare evaluations of alternative policies? If we don't have any idea why these transformations of the data are occurring, I don't think it's so obvious how to think about that question. So I want to propose a different approach that I think at least gives us some interesting possible answers to those questions. Yeah.
Just on the previous slide, the first point, you call these utilities, nonlinear utilities, distorted values, but there might
They don't actually call them utilities. Kahneman and Tversky are careful not to use that term.
People do, and there might be very good reasons for risk aversion in some settings. If, for example, you have limited wealth, as most of us do, you want to be careful not to use that wealth up or put yourself in danger of using wealth up, and there might be some settings where risk-seeking behavior is good. If you could increase your wealth to the point where you could transform your life, that might be useful too.
Right. Well, I don't think we're necessarily heading in such different directions. What I would say is, the kind of explanation you're proposing is an explanation that assumes that people don't respond in a way that is precisely tailored to the kind of situation they're in and optimal for that situation. You're saying, well, maybe it's a type of behavior which is, in fact, pretty good over some broad class of situations. And they're not recognizing the difference between the particular situation they're in and other things in this broader class of situations. I think that's what
Well,
you're saying.
I certainly,
And I'm going to propose a theory of exactly that kind. And the way I say the structure of the theory is, well, you need to explain how people confuse different situations with each other, and that's going to be the role of saying they base their decision on an imprecise internal representation of what the situation is that they're in. And when you said, well, but maybe it's sensible for the class of situations, I'm going to explore the hypothesis that yes, they learn a decision rule which is well adapted to some class of situations that they face. But I'm saying that I think that kind of theory is interesting in a way that just fitting nonlinear transducers to the data with no idea where they come from, that it's more interesting to have an interpretation that says maybe we can explain what they're doing, what it's actually optimizing under an understanding of how they confuse different situations with each other. Exactly because it can then start giving you answers to questions like whether you should expect those things to be stable across environments or not, or how they might relate to something that you think would be a sensible basis for welfare evaluations. Whereas if they're just arbitrary things and you have no idea why the brain would work that way, then it's harder to know what you should think of these things. Okay, so the hypothesis that I want to get you interested in is a possible explanation of the different kinds of patterns I was just mentioning that are all going to follow in a unified way from a hypothesis that subjects' choices have to depend in only an imprecise way on the terms of the lottery that's been described to them. And to give this idea of decisions being made in an imprecise way more precise content, I'm going to in fact suppose that the decision maker has a choice rule which is optimal, subject to their choice having to be a function of the noisy internal representations of the data, defining the problem. And optimal, I'm going to explore the hypothesis that optimal means something fairly simple, which is it means it maximizes their expected financial wealth across some class of decision problems. And so it will matter what the prior distribution of possible decision problems are, but given that prior and given an assumption about the nature of the noisy internal representations, I'm going to ask for a decision rule to be optimal in a relatively simple sense, which is maximizing expected financial wealth, which in the case of small enough gambles, I think is a reasonable assumption. This is, of course, not denying that there are not sometimes decisions in life that involve bigger consequences, things that would actually, could be life-threatening in some cases. And of course, genuine risk aversion is relevant to things like that. But these experiments that I was referring to, say the Kahneman-Tversky type experiments or the Mosteller and Noji experiments, involve small enough amounts that I think that the hypothesis that optimality should mean basically something like maximizing expected financial wealth is probably sensible for those kinds of decision problems. So a comment about this hypothesis is that when I refer to noisy internal representations, I don't want you to think that I'm assuming that the decision maker has an inaccurate perception of what was said to them. In other words, that it is genuine sensory error. They misheard. The experimenter said if the gamble pays off, you get 12 cents, and somehow they thought 12 sounded like 9, and because their hearing is bad, they are interpreting it as 9, although you actually said 12. I don't think that perceptual error is likely to be too important in experiments of that kind. What we're assuming is that there's a constraint on the precision of the decisions being made using that information. So they heard the number 12, okay, and the number was put in their head, but they're going to have to retrieve a sense of how big that is, how big a payoff is getting 12 cents anyway. And it's that retrieved value that's going to draw on a semantic representation that's imprecise. Basing these responses on the noisy internal representations is going to imply stochastic responses, and that means that the assumptions that we're going to make about the amount of cognitive noise in the internal representations is going to be required to be consistent with what we observe about trial-to-trial variability in responses, and not just average biases. But our model is going to be one that implies that also risk attitudes, so systematic biases in evaluations, should depend on the degree of cognitive noise. And so the perspective that I'm going to argue for is different from what a lot of the experimental literature on choice under risk does, where people might fit stochastic choice models to experimental data, say stochastic versions of prospect theory, but where there are some parameters that are explaining these nonlinear transducers, how the probabilities or the monetary payoffs get transformed into some nonlinear distortion of the objective value, and then there's an evaluation. Prospect theory proposes a value to assign to a given lottery in a deterministic way based on those distorted values, and then the noise comes in purely at the level of comparison noise, and the parameters that specify the noise are completely independent in the way that they're entering the model from the parameters that are determining the degree of curvature of the nonlinear transducers. In the kind of theory I'm going to propose, the degree of nonlinear distortion in evaluations, they're going to be something that is doing something like the nonlinear transducers, but these nonlinear distortions that are coming from estimates of value based on the noisy internal representation are going to involve biases, the size of which depend on the amount of noise. And so there's going to be a tight connection, according to the theory, between the amount of noise in choice and the size of these departures from risk neutrality in choice. And so that's an important difference of this kind of theory. Finally, the particular way of specifying the noise in the internal representations is going to be important, and the particular choices that I'll be making are consistent with other kinds of evidence on the nature of imprecise mental representations, both a lot of studies of imprecise mental representations of numbers for the monetary payoffs, but also on imprecise mental representations of probability and frequency information, which is going to be used to motivate the nature of the noisy internal representations of the probability information. So first I want to show you some new experimental evidence from an experiment that I did with Mel and Zhang. This is again an experiment where subjects have to declare an amount they're willing to pay for an outcome of a lottery. The lotteries are all simple lotteries where there's some probability P of getting a non-zero amount X. But the X might be a gain and it might be a loss. In the loss case, they have to declare the amount they would be willing to pay to avoid having to pay the outcome of the lottery. So it's a random loss, and you ask them how much would they pay to avoid having to pay back to the experimenter that amount X. The experimental interface looks like this. They see the gamble represented visually. There are number symbols there. The X is that minus $22.20 or 0, and it's telling them they have an 80% probability of getting the loss of $22 or a 20% probability of 0 loss. And the probabilities are represented not just with the number symbols at 80 and 20, but the two bars, the relative lengths of the two bars are also telling them the relative frequencies of the two outcomes. So there's a visual as well as a symbolic representation of the relative odds of the two outcomes. They're making their bid. They're saying how much they would pay to avoid having to deliver the $22 if that outcome pays by moving a slider. And they could also see their bid represented symbolically. When they move the slider to this distance, it tells them that corresponds to bidding $18.75. Or they can look on the slider itself. They can look visually whether they're making a large or small bid. So we're letting them understand what they're bidding, either symbolically or visually, and we're telling them some of the information about the gamble visually as well as symbolically. And we incentivize their responses by having a BDM auction at the end of the experiment, and we tell them that the nature of this auction is such that they're going to maximize their expected monetary gain from the experiment by in fact bidding the amount that does represent, in their view, their best estimate of the value to them of the outcome of the lottery. Yeah.
This is in the lab?
Yes.
Could you give them access to a calculator?
No. So we're not encouraging them to think of it as a multiplication problem. We're wanting them to make their intuitive judgment about what they would bid for it. And we used numbers that were not round numbers. You ask, why is it $22.20? Why don't you tell them $20? And the reason is because that would encourage them to think it's an arithmetic problem. And we didn't, in fact, we wanted them to make an intuitive judgment of the value to them of the outcome of the gamble rather than viewing it as a math test. And so we were using non-round numbers. The reason for the slider is the same thing. We didn't want them to type a number because we thought that would encourage them to type round numbers as their answer. They would give a one-digit, just say, oh, I'll say $20, and I won't type more decimal places because it's easier to type, and we wanted them to continuously move the slider so as not to force them to privilege some small number of possible answers. Okay, and the interesting thing about the experiment is that we're going to vary the value of p across the trials. We have a range of different probabilities p of the non-zero outcome, a range of different values for the absolute magnitude of the outcome, both smaller and larger values of x, and the sign of x. We have as many loss trials as gain trials, and we're independently varying each of those three things independently of each other. And so we're interested in the effects of changing the size of p, changing the stake size, and comparing to the gains to losses, because the previous literature had discussed patterns of switching between risk aversion and risk seeking depending on each of those three things. And so we wanted to look more systematically at the effects of all three of those things, and do it in an incentivized study. So many of the things in the earlier literature, both the work of Kahneman and Tversky that I mentioned, the work of Markowitz, and a lot of the early papers in the literature were not incentivized studies, and so we wanted to do it in an incentivized study. We wanted to do more systematic mapping out the effects of varying p, the magnitude of x, and the sign of x. One of the new things we found that the previous literature hadn't discussed was there are stake size effects, but that the stake size effects are approximately log linear, as I'll show you. And also the importance of the stake size effects varies systematically with the size of the probability p, as we'll see. Oh, yeah. Oh, okay. So the answer is they get an endowment at the start of the experiment, and so they are only going to reduce the amount they take home of that. So I mean that's the way we get them to pay. Of course, the Institutional Review Board will not allow us to have an experiment where they might actually go home with having lost some of their own money from having done our experiment. No, it might, but as I said, I can't. However interesting it might be, I cannot justify doing that experiment to Columbia undergraduates. But we tried to do it in a way that they would understand and perceive it as a random loss, and I mean at least you'll see what they do. I mean, but it's I think it's consistent with them understanding it that way. Yeah.
I'm just curious, is there a particular reason why you decided to represent it visually as well, the probability and the magnitude?
Just that we want them to understand. So I mean, if you think that communication is more precise with symbols, you might think you should always just show people symbols. But since we're not sure that that thinking abstractly people are better at than at more concrete things, particularly in making quick and intuitive judgments, we wanted to make it as likely as possible that they are correctly understanding what the gamble is that we're presenting, and so we were by presenting it more than That's our goal. I mean, at least we're not interested in sort of just genuine failure to understand what we were telling them. We want to find noise, but noise in cases where they do see, what we're telling them, and then it's a question of how they're processing it. But having them just somehow misunderstood what was going on, we're less interested in. I mean, that happens surely in life, but that's not what we were interested in studying. Yes.
Were the bars like here, one horizontal and one vertical?
Yes,
In the experiment.
Yes, that was.
So why not make them both vertical or both horizontal, which means I can start comparing things. When you do it like this, it's very hard for me to compare.
Well,
for example, I could move it to the 24-20, and I will know how much it is, and then I'll sort of, when it's parallel to the 80-20, I can start playing with that. Once you do it vertical and horizontal, I really have to figure in terms of numbers, which is a very different experiment than if I do it.
well, no, but in real life, I mean, how many real decisions about gambles do you do physically in the way that you're going to use that kind of geometric reasoning to get the answer? Now, we think it's more realistic to make them do something that doesn't have, doesn't tempt them to use that interface.
You answer Thomas, they should not make computations, you want the gut feeling in some sense. You don't want to allow them any kind of tools to help them.
Well, we don't want to allow them tools that would be an artificial aspect of the lab setting that would be different from other cases in life when people have to think about gambles. Okay, another thing to point out about the experimental method that differentiates what we were doing from a lot of earlier studies like the Tversky and Kahneman one that I mentioned is that we are interested in the variability from trial to trial and what the subject will say when they're repeatedly presented with exactly the same decision problem. And a lot of the literature assumes you are trying to find people's systematic preferences, and you try to set things up where you take care to only get one answer to each decision problem, and you try to let them think hard about it and make sure they give you what they really think, and you want to record that and think you're learning their actual preference ordering. We're expecting noise. We're expecting that if we can get them to genuinely think independently again, having forgotten that they've already seen the same decision problem before, that we're going to see random variation. And so for us, it was important, as in Mosteller and Nogi, to use an experimental method similar to the one of Mosteller and Nogi from back in 1951. We are going to present each of the problems 8 times to each subject. If they see a given problem, they see that same problem 8 times during the session, but we randomly order, what values of P, the magnitude of X, whether it's a gain of loss, rather than presenting them related problems in a sequence or something of that kind. We want to encourage them to think afresh and treat these as independent decisions. Okay, so we're interested in the trial-to-trial variation, and I'll show you data about that. Okay, what specific values do we use? We look at 110 different lotteries. They involve 11 different values of P, 5 different stake sizes, and both gains and losses. Those are the probabilities and the stake sizes that we use. Some of our subjects evaluated 400 lotteries, and the other half of the subjects evaluated 640 lotteries. And there are some differences. The ones who did more questions in the trial have somewhat noisier behavior. That again is actually, I think, consistent with our view. This is all taking place in about an hour. So they're making fast decisions. We're encouraging. Again, we're not wanting them to think of it as an arithmetic problem. We want them to make an intuitive judgment and move on and answer another question. Okay, so what I'm going to show you for each of the 110 different lotteries, I'm going to show you a distribution of values for the ratio of the elicited willingness to pay to the true mathematical expectation. I'm going to plot the average of the log willingness to pay as a ratio to the expected value, averaging over the subjects bidding on that lottery, and also the standard deviation of that distribution of values of the ratio of log of willingness to pay to the expected value. So I'm going to show you both average biases in the valuation of the lotteries and trial-to-trial variability. And so this is what those plots look like. In each of these cases, the top row is when it's random gains, the bottom row is when it's random losses. Each of the columns is a particular value of P. Within each of the panels, the different stake sizes are the 5 different values shown on the horizontal axis. And I've plotted them with log of the stake size on the horizontal axis to show the sense in which the data look like there's a log linear average bias, departure from risk neutrality that one is observing. So one is observing some stake size effects, meaning that the ratio of willingness to pay to expected value is not independent of the stake size, but when one observes the lines not being flat, as over there on the left, say when P is equal to 60%, it's a pretty much of a linear relationship. Here is the corresponding things for lower probabilities, going down to as low as 0.05. So what do we see that we think is interesting about these distributions of bids? Well, one thing that's interesting, I think, is that the distribution of value of the size of bids conditional on the stake size is similar in both the gain and the loss domains. So if we look at these pictures, the relationships you see up here are very similar to the ones you see down there, although these were random gains, these were random losses. So there's a great degree of symmetry between what's happening in the case of random loss valuations and random gain valuations. What I pointed out before was that the subjects did not all see the same values of P, and so that's actually probably due to the fact that it's not the same people who were doing the lotteries where it was 20% and where it was 30%.
So if you can't learn anything if you compare it this way, why can you learn comparing this way?
Well, there are things that I think you do see pretty systematically, which is that in general the slope is getting steeper as you go from the right to the left. And that seems to be also... well,
And in the previous one, you had two
and so when we separate the two groups of subjects, we see, I mean, we can't measure it as precisely, but we see that for each of the two groups, that it's getting steeper for the low probabilities and flatter for the higher probabilities. Okay, so just to summarize what we see here, this expected value of the log of the ratio of willingness to pay to the expected value seems to be roughly an affine function of the log of the stake size, and always to have a non-negative slope, and furthermore to have a slope between 0 and -1. Negative. Yeah. Sorry, I meant negative slope, but not as negative as -1. It's always between 0 and -1. If we think that log linear relationship with the negative slope that we find over the range of values we look at would hold over a larger value of stake sizes, like the ones that in hypothetical lotteries that some of these earlier authors in the literature proposed, where they demonstrated the existence of stake size effects, presenting people with hypothetical lotteries involving a much bigger range of hypothetical monetary payoffs. If we extended our results to a bigger range, then we should in fact get the sign to switch. We extended this and we thought it was moving log linear, we would go from positive values eventually to negative values for bigger stake sizes, and that would satisfy the Markowitz pattern. We do find the Markowitz pattern for cases like this. Zero is the risk neutrality, and so we're switching from risk seeking to risk averse as we go from smaller stakes to bigger stakes, as Markowitz said, when P is 0.20. Over here we don't see the switch in the sign of the risk attitude, but it looks like it would be there if we extended it to large enough stake sizes, which those earlier studies with hypothetical payoffs did. Suppose low probabilities but really large payoffs, you would see a switch, as Markowitz said, from risk seeking to risk aversion, and the other aspects of the Markowitz pattern also, if we extrapolated these logical relationships.
Markowitz was independent of P.
That's right. And
Here it is dependent on P.
well, the strength of it is dependent on P. Where it is dependent on P, but the negative slope is consistent. So Markowitz, I mean, if we think the negative slope is there and that it would extend further, then we would in fact find Markowitz's qualitative pattern for each value of P. It's true that finding the Markowitz pattern, we're finding the Tversky-Kahneman pattern also. So Tversky and Kahneman say this should be risk-seeking, this should be risk aversion. We're finding it, and for the high probabilities, we're finding instead risk aversion and risk seeking. We're mostly below zero here. So we're finding their pattern, we're finding Markowitz's pattern, and they're both right, because Tversky and Kahneman is only have that sign if you don't extend the thing far enough. You would switch the sign, according to our finding, if you looked at a larger range of stake sizes. But if you look at a certain range of stake sizes, Tversky and Kahneman are right.
Well, maybe you should show the other panel that P equals 0.90,
Yes.
not 0.1.
Yes.
Yes,
So,
this one.
these are definitely below zero, although again, there's a bit of negative slope, so it's consistent with the view that if you extended this enough and you thought the log linear relationship held, you would in fact flip the sign in a Markowitz way. So anyway, you can theoretically reconcile. It's not that the Markowitz claims and the Tversky-Kahneman claims are necessarily inconsistent with each other. There's a slightly more refined version of what you might think is true about those two things from these findings. Okay. What else do we find? I wanted to point out, after we found this log linear relationship, we learned from George Wu that there's a recent Gonzalez and Wu paper where they also elicit certainty equivalence for a wide range of values of both the probability P and the stake sizes, although they only use random gains. They don't look at losses. And they also only elicit a single certainty equivalent from each subject, so they're not learning about the variability. But they have 11 different values of P, but 15 different stake sizes, so a larger number of stake sizes than we do. They have 47 subjects that each value the same set of 165 different lotteries. And they only let each subject value a given lottery once. That's why they can do a larger number of stake sizes and have all the same subjects value in the same lotteries. And they do find, when we got to look at their data, this was not something they had made something of, but their data do show a roughly log linear relationship between the log of certainty equivalent to the expected value plotted against the stake size with a negative slope. So this is what the Gonzalez and Wu data look like with their different values of P and their larger number of range of stake sizes. Again, we find roughly log linear relationships. We find that they get steeper at the lower probabilities and flatter at the higher probabilities. So their data, they don't look at exactly the same things that we do, but there's a lot of consistency of what they're finding. The function has a higher intercept and a more negative slope for low probabilities than for higher probabilities. And the fact that the intercept shifts is, of course, consistent with the fourfold pattern of Tversky and Kahneman, but we find the stake size also matters, unlike what had been emphasized by Tversky and Kahneman. Finally, we find more variability in percentage terms of people's bids for small values of P than for large values of P, and we're interested in that and think it's related to these other differences between small values of P and large values of P. Okay, so how do we propose to explain what's going on in the experiment? So we have a model of decision making based on a noisy internal representation, where the model of noisy internal representations is of the following form. The information presented to the subject is a value of P and X on each trial. Those are going to be encoded by internal representations, R sub P, the representation of the probability of the lottery paying off, R sub X, the representation of the stake size. We suppose RP is drawn from some probability distribution that depends on what the P was presented to the subject. The payoff magnitude is going to be represented by Rx, which is a draw from a particular kind of distribution. We assume it's a Gaussian distribution, the mean of which is proportional to the log of the stake size, and the variance of which is independent of the stake size, but it may depend on the probability of the payoff. And we suppose it may depend on the internal representation of how likely the lottery is to pay off, and we're going to end up having a theory of how that would vary. But given that endogenous precision, then the internal representation of the magnitude is going to have this form.
Is there some evidence to support that people first look at probability and then at the amount? Because I would say, I would suspect that they first look at the amount, that's the first thing they want to know.
Well,
Probability is something more complex that comes next.
but I'll explain why the theory that assumes this is going to make predictions that look like what we see happening here. We'll see it.
Whereas the dual theory will not.
What?
Whereas the dual
And
theory
I
will
think
not.
I think we're not. That's right. So if you ask why do we assume this particular mathematical model of the noisy internal representation of the stake size, this assumption that the internal representation is drawn from a distribution with a mean proportional to the logarithm of the stake size means that we have similar degree of discriminability of monetary payoffs that differ from each other in a certain percentage amount. Which means we have something like Weber's law in perceptual psychology applying to the discrimination of different monetary amounts. That's consistent with some evidence. A particularly interesting piece of evidence, this is a study I mentioned in my last lecture, the study of DeHaye and Marquez, where they looked at errors in people's recalls of monetary prices they had been told for items before, and that study finds that the amount of error is similar in percentage terms for items with small prices and items with higher prices. And so that would be consistent with a model where the retrieved value from the internal representation is being drawn from this normal distribution with a mean proportional to the logarithm of the amount that the subject had been previously told. Okay, we're going to suppose that the sign of x people are able to retrieve without error. So whether they're talking about gains or losses, we're assuming there's going to be no confusion about. The information is encoded by these internal states Rp and Rx, and the fact that we're allowing the precision of the encoding of the payoff magnitude to depend on the likelihood of its being relevant to the outcome for the subject is motivated by a recent paper by Vandenberg and Ma, which is a study of working memory, in which subjects are shown different visual stimuli at different locations, and then they test them later on whether they can remember what color was presented at a different place in the visual array, and they don't know in advance which of the locations they're going to be asked about. What they show is that when they change the probabilities that they'll be questioned about different locations, that people's precision with which they can recall colors that they were shown at a particular location, there's greater precision in their answers about locations that they're questioned about more often, and less precision in their ability to answer questions about the locations that they are more infrequently asked about. So an interpretation, and indeed the interpretation Vandenberg and Ma give to that, and in their model of working memory that they fit to their data, is a model where there's a noisy retrieved memory of the color that was presented at a given location, but the precision of that encoding is different at different locations, with greater precision in the case of things that are going to be relevant for you to know about with greater probability. And we're going to assume...
Are you assuming that the variance is decreasing or
well, we're going to endogenously derive what it's optimal for it to be like, but it's going to be optimal for it to be decreasing in RP. And then that's going to fit the experimental data. So we're going to have a theory about how it varies with RP, as they do. So they have an optimizing theory in which it proves to be optimal for the precision of encoding to vary with how likely you are to be asked about that location. They have a cost function for precision, and we're going to use their cost function. So the same cost function that fits their data on endogenously optimal precision in working memory, we're going to use to derive our prediction about this optimal precision of encoding of monetary magnitudes in our model. Okay. What?
That probability is the frequency of seeing things.
Yes.
Your probability is the probability of one event of getting a prize.
That's right.
So
But if you ask
how
how much it matters to know in your decision, to pay attention to how big the monetary payoff was, it doesn't matter as much if you're unlikely to get it, as if it's something that will occur with a high probability. In any event, we derive the optimal thing. I'm not saying you have to believe me. We write down the cost function for precision, and we derive the optimal dependence of.
Are the participants aware of these patterns that show up? Something conscious or?
We have no reason to think they are consciously aware of it, but we're interested in the hypothesis that they have learned to do something that's reasonably accurate for them. It's not because we think they understand it and they're doing the calculus problem in their head to figure out how to optimally adjust my precision of encoding. We're assuming they can intuitively do something that works pretty well for them. Okay. More specifically, what we assume about the internal representation of probability is that what people encode is the relative probability of the two outcomes. We suppose this RP is also a draw from a normal distribution, the mean of which is the log odds of the two outcomes. If you remember, we visually presented the relative size of those two probabilities by the lengths of two bars. We think that people are, in fact, representing then what they're being told about the relative probabilities of the two things as an internal representation of those odds. And the idea that there's uniform discriminability of nearby cases according to how much they differ in the log odds is also something that there's some evidence from in other literature on the accuracy of people's perceptions of probabilities and of relative frequencies. Larry Maloney at NYU has a couple of interesting papers specifically arguing for this linear in log odds model of mental encoding of probability or frequency information. And so we're adopting that kind of model here based on that literature. Finally, our model does include random response error, and we're going to estimate then how important it is. We allow for randomness in subjects' responses even as a function of the internal representations, and the way we model that is by assuming that the announced bid of the subject is drawn from a log normal distribution. The log of the subject's bid is normally distributed with a mean, which is some function of the internal representation of the lottery, and has a variance which is independent of the characteristics of the lottery. This mean, the way it depends on the Rx and RP, we're going to assume is optimized to maximize the average financial reward of the subject. So the endogenous precision of the encoding of the monetary amounts is going to be optimized. The mean of this bidding function as a function of the internal representations is also going to be optimized. We're assuming the subject has no choice about this amount of this error in the randomness of their bids, given their intuitive sense of how good, how valuable, or not valuable the given lottery is. If you ask why do we assume the log normal distribution of bids, it's again based on this idea that their perception of the value of a certain monetary amount is imprecise, and imprecise in this Weber's law. Well, the difference, the degree to which they accurately recognize the difference between two monetary amounts depends on the difference in their logarithms.
Mike?
Yes.
So this mu c is what you called before late mode.
Yes.
So why
And
was it necessary to add it?
it wasn't necessary.
No, to fit the
We ask whether we fit the data better adding that parameter, and the answer is we can estimate the value of it. We do conclude that there is some noise of that kind. But I mean, we ask whether the data fit better if we set it to 0, but the answer is no. Yeah.
Your normality assumption and assumption, the functional form.
Well, the functional form of f is going to be optimized. We don't make a theoretical assumption about the f. The f is going to be can be any function. We'll solve an optimization problem to determine
But
it.
the assumption that the log of the W is equal to
that's this Weber's law thing that we were motivating by referring to the evidence on the errors in recollections of prices, for example. So suggesting that
If you generalize this to any sort of distribution, would you get a qualitatively similar result, or does this particular
I think qualitatively similar. This one is going to predict exactly that you should have that log linear relationship that we found in the data. So if you ask, could you understand theoretically why those plots were linear when we plotted logs against logs, this theory that assumes the log normal model of the encoding of monetary amounts and the log normal errors and also in the monetary bidding is going to give us exactly that log linear model.
then there might be a deeper question, why in our
No, that's right. That's right. But it seems that's not specific to gambles. That's something about processing numerical amounts in other contexts as well. Okay, so finally, the part that's optimized. We're going to have both this function and this nu squared, that was nu squared x. Sorry, the x is missing. The precision of encoding of the monetary payoff depending on what the representation of the probability of the non-zero outcome is. Both of those functions are going to be then derived as a solution to a minimization problem, which is minimizing the expected value of two terms. One is losses from a bid that differs from the expected value. And because of the incentive scheme with our BDM auction and the uniform distribution of bids by the computerized player, we can show that maximizing expected financial reward of the subject is equivalent to minimizing the expected value of the squared difference between the bid and the correct mathematical expectation of the lottery, conditional on, it has to be, of course, conditional on the internal representation. So that's what that objective is. That would be the only thing you want to minimize the expected value of if you were only choosing these functions to maximize expected financial reward. We assume, though, that there's a cost of precision. So there's a second term in the objective function which is linear in the precision of the internal representation of the monetary amount on a given trial. And that cost function, assuming that the cost of precision is linear in the precision of the internal representation, is the thing that works in the Vandenberg and Ma paper to explain the endogenous variability of the apparent precision of working memory in the different locations. And so we're assuming that same cost function here. So with these assumptions now, we have another free parameter, but just one free parameter is the way we're specifying what determines the precision of the encoding of monetary amounts. Finally, we have to evaluate these expected losses under some prior, and we're choosing the functions to be optimized for a prior that's a log normal prior over magnitudes, and that the distribution of log odds is some uniform distribution with these bounds. So we have two parameters for the priors that have to be implicitly learned by the subjects and that they're optimizing their responses for. There's a location parameter and a variability parameter for each of those two priors, but those things are not free parameters that we use to fit the data. We fit the values of mu x, sigma x, mu z, and sigma z to maximize the likelihood of the values of p and x that we're actually using in the experiment. So those things are not free parameters. The free parameters that we have to fit our data are the nu squared z. That was the precision parameter for the internal representations of probability, relative probabilities. The nu squared c, that's the parameter that Rava doesn't like, the noise in people's responses. And a was that multiplicative parameter in the cost of precision and the representation of the monetary amount. So we have three free parameters. We have 220 data moments. We're going to fit the three parameters to to maximize the likelihood of the data. And so now the blue lines are again the data I showed you before. The red points and the error bands around them are the predictions of the theoretical model when we fit those three free parameters. And so this is showing you the extent to which with those three parameters we can produce predictions similar to what's in the data. This is when we go then to the lower probabilities. So what does the theoretical model predict? In what ways is it similar to the data? It does predict a log linear relationship. It predicts that this should be a negative slope and should be linear when we plot logs against logs. It predicts correctly that the negative slope should become more severe as we go to lower probabilities, and it's making predictions about the variability that are also varying with the probability in more or less the way that it does. I have to see if I have a little bit of time maybe to give you some idea of how the model works. So why can the model explain the data to the extent that it does? So we have our log normal model of response errors, which implies that the optimal bidding rule to minimize that objective function that I showed you before as a function of the internal representation, this is the vector of Rx and Rp, implies that that optimal median bid is going to be the sum of three terms. This is the log of the conditional expectation of P conditioning on the noisy internal representation of the relative probabilities. This is the conditional expectation of the stake size conditioning on the noisy internal representation, the Rx and the Rp. And there's a constant here because of optimally correcting for the log normal error in your responses. So you should shade your responses because of the presence of that response error. And if we ask furthermore what this term should look like, this conditional expectation giving the model of our log normal model of noisy coding of the monetary payoffs, and I assume the log normal prior that the thing was being optimized for as well, that's going to imply that we can solve in closed form for what the joint distribution of the stake sizes and the internal representations are, and ask what this conditional expectation is. And this is the standard result on the expected value of a normally distributed variable conditioning on some other variable where the two variables have a jointly bivariate normal distribution. And so we're going to get that the conditional expectation of the stake size conditioning on the internal representation is going to be a weighted average of Rx this is missing logarithm. Sorry, we should say log. This is the logarithm of that. The logarithm of that is equal to the weighted average of these two things. A weighted average of Rx, this internal representation. This mu bar x is in fact the log of the prior mean of the stake sizes under the prior. So it's a weighted average of the prior with the log. This is log of x.
This is the log of expectation or expectation of the log?
This is the log of the expectation.
Log x, that's your variable.
No, I think you're right. I think it's in here. I think it's the expected value of log x. The expected value of log x is a weighted average of the Rx and the mean of log x under the prior, and the relative weights is going to depend on the precision of the encoding of the monetary amount relative to the amount of prior uncertainty under the prior about what that amount is. And this gamma x parameter is going to depend on Rp if the nu squared x depends on Rp, which it'll turn out that it will. We're going to allow it to depend on Rp. We determine how it's optimal for it to depend on Rp, and will in fact vary. So the gamma x will vary with Rp, and that's going to be the thing that's going to make the slope of those log linear plots different depending on P. So the model is going to then imply a log normal distribution of bids, where the mean, because of the things on the previous slide, is going to be a linear function of conditioning now on the true x, and on RP is going to be linear in the log of the true stake size, and it's going to have a variance which is independent of the stake size, but which is going to depend on the RP, because the RP is affecting both the mu squared x and the gamma squared x. So you see that this the mean of this normal distribution is linear in the log of x, and it's going to have a slope between 0 and 1, because its slope is that gamma x. Gamma x was this thing, and it's between 0 and 1.
Mike,
Yeah.
in the delta, the mean of the prior is in the delta.
Yeah, the delta collects several constants, but it's,
including it.
yeah.
And when you pick numerically, how do the means compare? The different nodes, how large are they? When you fit the data.
I mean, there is significant variation between the low P's. The thing is, we don't see the RPs, so we get to see the averages, because what we see is what they seem to be on average for different values of P. But so I'm getting to that. So this is conditioning on a particular value of RP. We have this log linear relationship. Now if we want to condition on the true characteristics of the lottery, we're going to condition on x and a true value of P. But this expected value of that, of the log ratio of the bid to the true mathematical expectation, now conditioning on what the true lottery characteristics are going to again be linear in the log of the true stake size, where now this gamma is not that gamma x, this is an average of that gamma x, averaging over the different RP internal representations associated with a given true value of P. And so now if I ask you what the thing should be that we plotted in the figure is actually I have lost, this should be again this thing divided by the expected value. Switch. This should be down here, and that should be up there, because it's this one that has the gamma P in it, and then when I put that in the denominator, it's going to become minus 1 minus gamma P. So it's going to predict that this should be a negatively sloped relationship. The slope should be minus 1 minus gamma P. This is a quantity between 0 and 1 with a negative sign between 0 and minus 1.
And where does the log come from?
Where does the log P come from? It comes from right here. This is in the denominator. I told you those things are switched. This is expected value of the log of the ratio willingness to pay to the expected value, which is what we were plotting on the previous data plots. Okay, so we predict that it should be a log linear function with a slope between minus 1 and 0. It should be the same function of P and of the stake size, regardless of whether we're talking about gains or losses, and that's what we also saw, approximately true, and we test statistically whether we can reject the null hypothesis that they're saying, and we argue that there is, that the data are quite consistent with symmetry between gains and losses in that respect, and the theory says there should be a steeper negative slope the less precise is the encoding of the monetary payoffs. Because less precise encoding made the gamma x smaller, and this gamma p is the average of the gamma x's for the internal representations that occur in the case of a particular value of p. So now we need to connect the precision of the encoding of monetary payoffs to p, and we find, I'm not going to show you the algebra of that, but we discuss it in the paper, how we can solve for the optimal degree of precision to minimize that objective I stated before. And we find that it is indeed optimal to choose lower precision. The smaller is RP. Low values of RP imply that P itself is likely to be smaller, although there's a distribution of possible values of P associated with a given value of RP. And so then that's going to connect P to the average degree of precision of encoding of magnitude.
With payoffs, so the theory that is going to predict that lower values of the probability of a non-zero payoff is going to be associated with more variable internal representations of the monetary payoff, which should result in more variable bids when P is smaller, more variable bids in percentage terms, and a steeper negative slope of that log linear plot
As a function of log x, which is also what we found. And we found both of those things in our data. Finally, under our model of the noisy encoding of the probability information, we find that this delta P minus log P is predicted to be a decreasing function of the value of P, and that explains how the intercept of the log linear plot shifts with P, which was explaining another salient feature of the experimental data, and in particular is the main thing that results in the Tversky-Kahneman pattern. Okay, so I want to very briefly say something about another kind of recent evidence that I think is at least very suggestive that a theory like this could be on the right track. If we have this noisy coding interpretation, something that you might think is a big problem for the theory, is that this is a theory that says people should systematically deviate in their valuations of lotteries from the true expected value of the lottery, but it's an explanation for it that doesn't have anything to do with genuine attitudes toward risk. So we're saying that it's actually just reflecting imprecision in people's intuitive judgments about what the expected value is. And they're told the probability P, they're told the monetary outcome X, and we're just setting them in a situation where we're asking them to produce intuitive judgments of the products of these things, and this is a theory about what kind of biases you should expect to be in their intuitive estimates of that product. Doesn't have anything necessarily to do with risk, and so you might ask, shouldn't similar biases appear if people need to, without using a calculator, estimate the product of P times X, even if it doesn't have anything to do with risk? You're just going to give them P times X. So Ryan Oprea has an interesting recent paper where he does that. He asks subjects to bid a certain amount. He elicits their willingness to pay for getting a fraction P of a monetary amount X, which they're going to get for sure. So there's no gamble involved. It's just that instead of telling them what the amount is, he said it's fraction P of the amount X. And he calls that the simplicity equivalent of the problem defined by fraction P of amount X. That's analogous to the idea of a certainty equivalent in the case of the lottery. So what simpler stated monetary amount are you indifferent between, and this more complex statement of the monetary amount? And he constructs what he calls deterministic mirrors of lottery valuations problems. So he actually has the same subjects both answer questions about lotteries, where you can get an amount X with probability P, how much do you bid for that? And he asks the same subjects on other trials, how much would you bid to get a fraction P of the amount X? And he uses the same P's and X's on different trials, and he can compare subjects' behavior when it's simplicity equivalent of a deterministic problem and when it's the certainty equivalent of a genuine lottery. Okay, so here's his data. So the way he's plotting things, the value of P are the different points on the horizontal axis. On the vertical axis, he is, as in the work of Enke and Graeber that I showed before, he's plotting the certainty equivalent, elicited certainty equivalent as a ratio to the X. The X is $25. So this is the ratio of certainty equivalent to X, and he wants to compare that to the P. So perfect risk-neutral valuations or correct valuations in the case of the multiplication problem. Correct answers or risk-neutral answers if it's the risk question mean you should be on the diagonal, and he finds systematic departures from the diagonal. There are two cases, the lotteries, he's eliciting certainty equivalents, the deterministic mirrors of those same lotteries, he's eliciting what he calls simplicity equivalents. And the data with the lotteries is exactly what I showed you before from Enke and Graeber, right? Overvaluation of the lotteries when P is small, undervaluation of the lotteries when it involves random gains when P is large.
larger. This is the corresponding thing when they're random losses rather than random gains. So that's Kahneman and Tversky's fourfold pattern of risk attitudes here versus here, and here versus here. But now the red data are the same distribution of bids when it doesn't involve risk at all. It just involves how you value getting a certain fraction of a monetary amount. It's a very similar pattern. You get the fourfold pattern of biases, and even the quantitative magnitudes of the biases are not terribly different in the case of the two kinds of problems. So, you know,
People ask both the certainty question and the simplicity
yes,
question.
on different trials, but
Different trials, which order? I mean,
I
suppose you just ask simplicity. No, don't put any risk inside. Still you get this picture?
he what? Yeah, I think he alterates the order. The question is, again, I don't know if he did the thing of having subjects that never heard about risk
About
to
lotteries.
see if they can
Because
multiply
some
with
of-
it.
Some of people by now they're always asked about lotteries, and by now people that are fresh never heard about lotteries. Ask them simplistic questions, still get a good pattern. I must say it's quite surprising.
Well, I thought it was amazing, but I mean, you know, there's at least there's a simple interpretation of what could be going on there. What? Oh, because I had a theory before I saw the results. I had a theory that would have predicted exactly that. What? Well, that's because I think people can do mental arithmetic when it's simple enough.
One half
And
they
of
do
course,
okay. The problem is 10% of $10. That's where they
So-
that's where they have to have it. Yeah. Sounds yeah.
So I do not deny the possibility of mental arithmetic when it's simple enough. The question is whether people have an ability to also form intuitive guesses about the rough magnitudes of things when they are not. You know, it would be too much trouble to write definite multiplication on a piece of paper and actually do the multiplication. Again, I would not have said I was sure I would know what would happen, but that it's right.
On the simplicity we are talking.
Again, I'm sure that you could give people problems where it would not happen. You know, the thing you said, you know, you get a $10, you get half of $10. What do you think you would bid for it? I mean, it's easy enough, but I think they know they can figure that out. And they would, you know, not having to be forming this intuitive sense about how big is $10, about how much is a half. But I think that people have this mental ability to form intuitive judgments without doing arithmetic. I think this is a plausible kind of bias in that when they're. I'm not as suspicious of them as you are. I didn't say the probability is 1. I'm saying I'm inclined to think. Yes. This is purely an arithmetic problem. It is nothing but an arithmetic problem. Well, but you know, this is also known to be true with risk choices, that people with better math skills are found to be closer to risk neutrality in their judgments about the lotteries too. So I mean, yes, I believe that numeracy should affect this, but I'm not sure that it affects the one problem a whole lot more than it affects the other. I mean, that would be an interesting thing to know, but yeah.
It's a calculation problem, but framed in a very strange way. If you ask them explicitly, multiply 25 by .2.
Well, if it's an easy number, I mean, I get. Yeah, no. The point 2 is easy. Well, the question is whether they gave them something that was easy to multiply by 2. Okay.
Okay, so I guess I'm out of time, but again, we'll post the slides. There's some other, there's some reference to other interesting results that you should know about. I'm going to mention Miguel, who is here, has done interesting work in his dissertation that is mentioned on one of these later slides, where he shows that the amount both of randomness in people's choices in gambles and their degree of departure from risk aversion correlates with measures of the precision of their number representations, which he measures two ways. One is by having people make judgments about the relative sizes of visual arrays and looking at the accuracy of their behavior responses there. The second and more complicated one is by looking at the ability of researchers to decode what number someone was being shown when they were in the brain scanner purely from the brain scan. And he finds that the subjects differ in the degree to which the number representations can be decoded, and that correlates with both the variability and the apparent degree of departure from risk neutrality in the subjects. Again, at least a very intriguing finding, and people that are more interested in that should ask Miguel, because he knows a whole lot more than I do about exactly how he did it. Okay, so anyway, I hope to convince you that there are a variety of aspects of measured risk attitudes that can be explained by a unified model, and that uses methods that are similar to the ones that have often been used to explain biases in perceptual judgments. That suggests that risk attitudes might be often better viewed as a sort of perceptual bias rather than an actual aspect of people's attitudes toward risk or their preferences. As in perceptual domains, I would argue that it's important to be modeling the variability of people's responses and the average biases of their responses jointly, because I think there is evidence that the two things interact a lot with each other. And I've suggested here that the nature of the imprecision in the subjective coding of monetary payoffs might be similar to what's observed in the coding of numerical magnitudes in other contexts. And if so, economists have something to learn from studying a larger literature in psychology and neuroscience in informing the way we should develop our models. Thanks.
Mike, you didn't come right out and say it, but it sounds as though the implication of this point of view is that Kahneman and Tversky are not critiquing expected utility theory at all. Their work has nothing to do with attitudes towards risk, but it's all.
I mean, I'm proposing, I can at least explain findings that are very much like theirs. They're very consistent with theirs, with a model that.
But in which case, their interpretation of the results was wrong.
I mean, I'm at least supplying different shading. Saying is it wrong or not. I'm at least hoping that you understand it better from when I show it to you from this angle.
That's why I said you didn't say it, but it sounds as though the implication.
I hope that the literature moves forward. That we obtain more refined interpretations over time. I mean, whether one says that means the earlier things, were completely wrong is a different thing. I mean, I would never have done this if I hadn't thought a lot and taught their work. It made me have an idea what kind of patterns I was trying to figure out an explanation for. And so it's not that I didn't, and in our experiment, what we find in the experiment is pretty consistent with the things that they claimed were systematic regularities as well. So it's not that I'm, sort of saying that the regularities they found aren't there, and they said that we're just offering a descriptive model.
But they were also they said quite explicitly that expected utility theory was wrong.
Right. Well, so right. And so I am not endorsing everything they said in the spin they gave to their findings. But you could equally view this as an explanation for what prospect theory is really about. Deeper foundations for why something similar to what they were hypothesizing is there, but has an explanation that they hadn't yet seen.